For decades, science fiction promised us robotic assistants that could navigate our homes, cook our meals, and fold our laundry. Yet, as we look around our actual living spaces, those versatile, all-purpose machines are nowhere to be found. We certainly have robots. As you see on this modern factory floor, massive assembly lines are filled with powerful industrial machines executing complex manufacturing tasks. These machines operate with incredible speed and millimeter precision. But they share a severe limitation. They only function in completely controlled, pre-programmed environments where every single variable is strictly regulated. The real world doesn't work like that. Inside human homes, bustling, busy offices, and dynamic modern assembly lines are unpredictable, chaotic variables where objects move and nothing stays exactly where you left it. Because traditional robots run on hard-coded instructions, introducing a single unexpected variable, like a chair pushed slightly out of place, causes the entire system to fail. Researchers are now focused on building machines that learn to adapt to these variables on the fly, the core objective of physical AI. The foundation of this shift relies on a different software approach. Tech leaders and startups, including divisions like Google DeepMind's Gemini Robotics, are moving away from traditional rule-based coding. They are replacing rigid scripts with multimodal foundation models. These act as digital brains capable of processing multiple types of inputs, like sight, sound, and touch, simultaneously. Instead of blindly running a code loop, these models use an array of spatial sensors and neural networks to keep a constant stream of data streaming in from their surroundings. By analyzing this information, the robot can reason about the physical world, distinguishing between different objects and figuring out how to interact with them without a step-by-step manual. This multimodal brain allows the machine to interpret its surroundings, moving past the limitations of simple, repetitive execution. If engineers aren't writing millions of lines of code to tell the robot how to pick up a mug or open a door, how do these new brains actually acquire their skills? The solution is a process called imitation learning. This approach moves away from running billions of virtual simulations and instead pulls training data straight from the real world. Robots learn by directly watching humans. They record and analyze the highly variable ways people perform physical tasks, such as folding laundry, and map those organic movements to their own hardware. Automakers like BMW are already testing this technique. They are placing general-purpose robots on actual manufacturing lines, where the machines learn by observing the human workers next to them. By mirroring human experience rather than waiting for humans to write flawless code, these machines bypass the primary bottleneck in robotics, allowing them to scale their abilities at a rapid pace. There is a strict geographical reality to robotics. If a machine needs to climb our stairs, use our tools, and navigate spaces built exclusively for human bodies, the most efficient solution is to adopt a human form. Humanoid development relies on intense mechanical precision. The Boston Dynamics Electric Atlas, shown here, demonstrates the complex actuators needed to mimic our own movement. Other models, like the Tesla Optimus, conceal that mechanical complexity behind smooth, consumer-ready casings designed for integration into everyday spaces. But placing a 150-pound machine built of heavy, rigid metal joints into an unpredictable domestic environment introduces physical safety hazards. To mitigate this, engineers are focusing on dexterity and softness. They are adopting multi-actuator robotic hands layered with synthetic skin, allowing the robot to handle fragile objects and safely interact with people. A highly intelligent software brain serves little purpose without a physical body designed to safely absorb the bumps and impacts of living alongside us. We are exiting the era where machines were bolted to factory floors and contained within safety cages. The shift toward adaptable physical AI is well underway. By combining multi-model foundation models that understand their surroundings, imitation learning that mimics human action, and soft robotics that prioritize safety, engineers have built a framework capable of operating in unstructured chaos. The physical boundary that has historically separated the world of machines from the messy world of humans is dissolving. The future of the field rests on building machines that learn through direct experience, finally allowing them to navigate the real world with a sense of touch and understanding as naturally as we do.